Welcome everybody to our next video for our Lab 5. Lab 4 certainly evolved to be somewhat interesting with some of the unexpected issues that arose, but I think it's a good thing that it happened that way because it gives us an opportunity to really focus in and learn about the stack pivot before things get a little bit more complicated. So that way we can make sure we really do have a good understanding of how a stack pivot works and some of the different options that are available to us. It's easier for something like that to kind of get lost into the grand scheme of things when you have something a little bit more grandiose, such as ROP. But in any case, with Lab 5, we will be going deep into ROP. So we'll present you with a somewhat challenging lab to test your abilities, and you'll have an opportunity to work with the same 2 or 3 person group as before. I would caution though that I do recognize that some students, the range of capabilities can vary, so that's one thing. And secondly, some students are just very gung-ho about starting early and doing a ton of work on their own, and so they may usually finish things very early. Just keep in mind that you are with a group here, and part of the reason for that is just because this is somewhat challenging material, and I just want to make sure that people have the opportunity to learn it well and to be able to consult with their partners if they're feeling lost and confused. So if you do have the inclination to finish very soon, you'll still need to work with your partner, and I would ask that you don't share the answer, quote, quote, that you may develop in a day or two if you're working, very hard, very fast, just because that would deprive that individual of the ability of going through the process. And these are skills that the people do need. So we'll have other labs where you will need to be able to do this on your own. Particularly for those of you who may be doctoral students, you absolutely need to master this content. But even for those of you who are master students, you'll still need to be proficient at these skills so that you can do it successfully on your own. So work well with your partner. Just make sure that you don't let your partner do all the work, because then that would again deprive you of the chance to get those skills that you need. Alright, so let's get on with it and see what's up with Lab 5. Okay, so I have selected a target for us called Easy MPEG to DVD Burner. So this is the target, and I'm going to help get you started. Our focus here is on the ROP aspect of it. So let's take a look here and see what we have. So I provided a sample script just to get us started. We have an SEH overwrite just to get us started. And this is one that you can use to get started, but you absolutely cannot use this, so you'll need to use something different in your actual script. So we can save this, and we can go ahead and produce the output. And we get our output right over here. And as you can see right here, might as well just close out of this. We have all A's and just the SEH overwrite address. So what we want to do to cause this is we go over here, we put it into username, and by the way, of course, we do have this. Actually, I guess we don't have it attached, so that probably would be a good idea to attach that. Then our G for go once again. And so now we just simply hit OK, and we get an SEH overwrite. That's our address right there. So we can go ahead and set the breakpoint for that there. And let's see what that is again. So essentially this is adding 778 hex to ESP. Now if we recall from our script here, there was no NSEH, just an overwrite, all A's, and then an SEH. For this type of SEH overwrite, when we're using it to bypass DEP, and when DEP is in place, this is the more traditional way of doing that, is we just have an add ESP, and then that'll take us to wherever our ROP chain will begin. Right now there is no ROP chain, so that will be an exercise for you guys to complete. So we can go here to ESP, we see our ESP, can we find our A's? Up there they go, there's a huge assortment of A's, and at the very end there we have our address. So that's our SEH overwrite, and once we get to this location here, we can simply add that to ESP. And so there will be some adjustments that will occur before that happens. So we'll go ahead and see that. And so right now those are the adjustments. So once we actually went into the exception handler, then there were adjustments to the stack, so that the ESP plus 778 gets us to that location right there. Now obviously right now we just have I'm not sure what I just did there. No control Z, but that's fine. You know, well, this is the location where we'd have the ROP chain. Now granted, you guys will need to use a different SEH overwrite, and we'll talk about that in a moment. And so we can continue on, and now this actually happens. So we can go there, and we see ESP is right there. So this would be where the ROP chain would initiate, and then the return there would get us to the next thing that we had as part of our shellcode or payload. But in this case, so it would have gone to right here, right? Assuming that the ESP hadn't changed since then, which it may have very slightly. But so these are treated as memory addresses. So this would be one gadget, this would be another gadget, this would be another gadget, another gadget. But because it's just 4141 and that's not a valid memory address because there's nothing there, then we get this exception. So obviously we'll need to place addresses there. So let's talk about some of the considerations that we'll need to be aware of. Notice that when we have this, we have ASCII. We take the ASCII and we paste it into our application. So that's going to limit some of the opcodes that may be available to us. It doesn't mean it's going to limit it as severely as with our previous Lab 4. It will be a little bit more liberal. You know, we can see some interesting things that may work. And one of your first steps, of course, is going to be to go through and identify the bad characters. So we worked through in one of our in-class activities how we can use Mona to enumerate bad characters, and it really just does it. You know, sometimes you may You need to do it multiple times to identify all the bad characters. But the bad characters for this one there's not very many of them, and they're pretty predictable, so that really shouldn't be too difficult to identify some of the bad characters. So we'll want to avoid our bad characters, but anything else that should be fair game. So this right here is our ROP chains, and I'm limiting you to Virtual Protect. You need to use Virtual Protect. You cannot use Virtual Alloc. So you'll need to work with Virtual Protect. And that may present some challenges. What are you going to do your Virtual Protect on? Well, it's probably, and this right now is me helping you to figure that out, by the way. It's probably going to be something on the stack, right? So what points to the stack? A little thing called ESP. Where on the stack will it be? Well, you know, that could be a mystery. But what you'll need to do with your ROP is to identify a way to mark out a region of the stack. Maybe you'll take that value, so it could be ESP at a particular location when the code's being run, size, however big you need your size to be. It could be 400, 600, whatever the case may be. Mona's default is typically 201, which may or may not be in here. But you'll need to modify that to accommodate what you have on the stack. So you'll need to figure out how to get the value off of the stack. So again, the region of memory that you're modifying with Virtual Protect is going to likely be dynamic. It's probably not going to be the same thing. And even if it were, then it could vary from operating system to operating system, as well as when the machine restarts. So we want to make sure that we do it in a dynamic fashion. So you'll just need to make use of ESP to figure that out. Sometimes EBP very often is going to be in relatively close proximity to ESP. At certain points they may be identical, or there could be the difference between them could be relatively small. So if for whatever reason ESP doesn't work, then maybe you could do EBP. So it could be, you know, you could have starting location ESP plus 100 plus 200, size 500, or maybe just ESP. So just keep that in mind as you are going through and working on your Virtual Protect. Again, that needs to be done in a dynamic fashion. When we go to do our stack pivots, if we notice right here, this is a relatively large stack pivot. So you'll be doing a similarly large stack pivot. And if we go to stackpivot.txt, this provides all the stack pivots for us. Again, we want ASLR false, and there's only 3 of them. One of them has nothing. This one down here. Skin Magic doesn't have anything that is large in size. So you'll really be working with ESP, MPEG, DVD burner. And so these are in order from small to largest. And there's a ton of the large ones, so we don't need some of the huge ones, you know, stack pivot 17,000. That's not going to be helpful for us. So it'll be relatively similar to the one in our example. So we can, you know, maybe find something around here. But really it's up to your creativity and, you know, whatever works. And there aren't bad characters. And there is one bad character, but that's okay because we're doing it with the SEH overwrite, and so we only need to use one of it. That just means that we can't have anything that follows it. So the SEH overwrite will be our final item, and we won't be able to add anything else to it, unfortunately. Now we could, trying to tab here, we could do that if we moving this up here. If we were able to make use of Skin Magic, because Skin Magic, there's no 0, there, it's 1, 0. But if you look at this, there really are not any larger ones in Skin Magic. They're all smaller ones. So, you know, that just really, I don't think it would probably work out too well using Skin Magic, because the largest Skin Magic one is, I'd have to check, but it's less than 100 bytes. All of the larger ones are going to be from the image executable itself. So, stack pivoting. And once we get to the place where we want to be after our initial stack pivot, we may use our NOP ROPs a little bit, because we may need to move up or move down, and that's fine. So what is a NOP ROP? Let's take an example here. So let's look at this here. So it's taking a random ROP gadget, and if I wanted to turn this into a NOP ROP or ROP NOP, I guess ROP NOP is what makes more sense, then I would just take this C3 and there you go. I have a ROP NOP or NOP ROP, whatever the case may be. Effectively, it just does nothing, but it takes up space. So you may need to do a little bit of that. Another possibility is if you're trying to move a distance rather than using a lot of NOP ROPs, you could also, or you just may need to do this for other purposes, which I'm deliberately trying to be vague here. You may need to do some smaller stack pivots. So it might be 12 or 16 or 20, whatever is appropriate. And it is possible to use more than one of them in a row. So you could have a series of 4 of them, one after the other, if it served a purpose. So, you know, just keep that in mind. That's a possibility that you can utilize. So we're back over here and we're restarting that, and we have our ASCII, and we see that it's, you know, it's taking some of these weird looking values and it's working for us. So just because it is ASCII, don't think that it's necessarily going to be, you know, a huge limitation. Obviously certain things like 00, the null byte, will come into play, but even some of our more bizarre looking characters like that ACK there, it just interprets it in that fashion. It'll go through and it gives us the value we want, so that's great. And again, you know, we can test for our bad characters early on. So I'm over here, I'm in my ESP and doing my EX chain. And do my breakpoint there. So, you know, this one right here is really the only thing there that I care about. So when you have Mona, it runs and it goes and generates stack pivots, and the algorithm, I guess in my opinion, is just somewhat lazy from a lazy standpoint. It gives you some excess garbage here that you really don't need, so you could trim it down to something like this. And of course you can't do that for this exercise. This add ESP 778 is off limits, whether you start here or you start here. But you could just start right there. So when I created the JOP Rocket, which is, you know, a tool that does a lot of this type of thing except for JOP, and that's one thing that I took care of. So, you know, we can trim the excess garbage, but, you know, for whatever reason in Mona we do see some of that excess material there. But in any case, back on track here, we can go ahead and get that added. So again, this is where we start things off, but we see that there's stuff that happens before and then stuff that happens after. So this region of memory right here, all these 4141s, is going to be where we have to work. So that means we need to fit our ROP chain there, we need to fit our stack pivot there, and of course we need to fit our shellcode there. And you know, I'm curious about ECX at this point. What ECX, EBP, are these useful to me? And let's see, ECX plus 0, and we can look at this. I don't think this will be useful. I think this is probably asking. Oh, not thinking straight here. So that's not really too useful, but you know, it doesn't hurt to just peek around. And I didn't really anticipate that was the case. EBX is still going to be on the stack. And these values right here, anything 76, 77, those are going to be system level APIs. They always are, so there's no point in even checking there. And then EIP is our current instruction pointer. So why am I over here and talking about this right now? Again, just to reinforce the idea of all these A's are things that this is the area that we have where we need to get everything. Just like what we've done previously before. We can't expand this because if we expand it, then the null byte is going to run into problems and our address just will not execute correctly, our SEH override. And you're welcome to test that yourself. Maybe you'll find a way that I wasn't able to find. So again, let me reiterate, the focus here is really on utilizing ROP in order for us to go ahead and bypass data execution prevention. And we absolutely must use Virtual Protect. We cannot use Virtual Alloc, which, I mean, you can use Virtual Alloc. I'm just artificially forbidding you from doing so. So in the sense that I would not give any points for using Virtual Alloc, you need to use Virtual Protect. So we do that, and then we get to our shellcode. You can use a simple benign shellcode. I'm not too concerned about that. We will be focusing more on shellcode later on. If you wanted to, you could also do a search in process memory and see where else this payload may be. I'm not sure. It could be in some other locations, but just looking at our registers, I didn't see any glaringly obvious ways to reach them. Although you never know until you try, so it'd be worth checking out. But just this right here should be sufficient for what you need to do. So that's all I have. I just wanted to kind of walk through some of the process. So, you know, the first step here is just to get the SEH overwrite going, get started with your ROP. I guess it's probably a good thing here to comment on it initially. Don't expect that just using Virtual Protect by itself, one of these predefined chains, is going to be sufficient, because that's not going to be the case. You know, one thing that I talked about clearly was the need to have, and this is not even the right ROP chain, this is an old ROP chain. Alright, that's better. So our correct one right here, you know, I mentioned before that we need to get it dynamically, get the value from ESP for where we need to modify that. So that's one thing that will be different. Can we see anything else that's going to be different? Well, I talked about the size being probably bigger. So obviously it's not going to be 201. 201 is just kind of a default. And then the no bytes. So no bytes are not going to work. The good thing is if you establish what the bad characters are, and you use that as input when you go and generate your ROP chain. So the PyMona ROP, and then you can specify on there the bad characters. And the MonaPython help guide online, which we've referred to a couple of times, that provides the syntax. So once you do that, then it should automatically generate some alternative ways of doing that. When I did this, I did not do that, so it just did it the plain, easy, simple way. But even if it doesn't, you still need to use Virtual Protect, and you can generate these on your own if you need to. So we could go over here and find gadgets to achieve the same effect. The same effect of loading the registers with the appropriate values, and then once that's done, then we do our push add. So that's the push add technique. You could do other techniques as well, which we've alluded to. So you could just push each value individually. You could push dummy values, like all A's for this value, all B's, all C's, all D's, all E's, and then go back and overwrite them. That's a little bit more complicated, and I don't really expect you to do that. Although I guess I haven't looked too carefully at the requirements for this, so it may be possible. So many different ways in which to do your ROP. But if you just try and do the most basic one like this, it's not going to work. Right here we have the no bytes. So just keep that in mind. Mona is a starting point, but you may need to do some additional work on your own, and that will be the case. So we got to figure out what to modify, how much to modify, and then once we do that, then when the ROP chain completes, so this ends right here, then maybe we could have, probably be a good idea to have a NOP sled. So let's figure out how this could look. So we could have like a NOP sled right here. So NOP sled would be X90, and we could make that, I don't know, let's say 10. And that just gives us a safety net. So if our calculations are off just a little bit, it doesn't really matter. And so we want the NOP sled to follow the ROP chain, or it doesn't necessarily need to follow it. So after the ROP chain, we could redirect it to wherever we want. So we could have a stack pivot to the NOP sled. However we get to the NOP sled doesn't really matter. There are possibilities. But in any case, once we get to the NOP sled after the ROP chain ends, we will know it's successful because it will interpret these as NOPs, as instructions. If it tries to go to address 90909090, and we get an error message, an exception, then ROP was not successful, because it's treating these as addresses rather than instructions. So when you're successful, it'll treat these as instructions. So in that case, we can place our raw shellcode onto the stack. So let's see what this might look like. So we can have our exploit. And this is just one possible way to do it. You can get much more complicated. So don't feel like you need to copy this, but it gives you something to maybe think about. So we could have some ROP chain there, maybe. And this is about as basic as it could be. We could have our NOP sled. We could have our shellcode. And then eventually we need to get to our SEH overwrite. But let's say hypothetically that the SEH needs to be, 2,000 bytes. So we could even call that SEH offset. We need the 2,000 bytes in order to have our SEH overwrite be reached. And if we go and count these and add these up, that's not 2,000 bytes. It's not even close. So we need to fill the space in order to have our SEH overwrite, because as it is right now, it's not going to happen. Now you could manually go and add all these up, but that would be kind of tedious. One thing you could do is you could, and this is a more clever way to do it, is we could have something like, say, A, which is 1 byte, and we could multiply that times, and then we could have, say, the length of ROP chain plus length of NOP sled plus length of shellcode. So all of those, and of course we would need to have the SEH offset minus. So 2,000 minus all of that. So let's say this ends up being 1,000. So that would do 1,000 A's. And then that would give us exactly, these right here then would exactly add up to 2,000, which would be what we would need for our SEH overwrite, which would be at the end there. So the point of all this that I'm sharing with you is distance matters, size matters, accuracy and precision definitely matters. So, as we develop this type of thing, we do it one step at a time, but we also have to keep in mind the big picture, and the big picture here is, SEH overwrite needs to live at a certain spot, and some of these other things may live in certain spots, and we have to find a way to kind of connect them all together and make sure that there's a happy medium in the sense that the distances are correct for certain requirements. This is one requirement here. Sometimes exploits may have other requirements. You could have multiple stack pivots inside of this. That's possible, and maybe you may need to do that for this. So you may need to have a stack pivot to jump over something, or to go backwards or go forward, and at the end of the day, everything needs to balance out. And the best way to do that is through trial and error. Set your breakpoints. Go in there and investigate in the stack or the heap or wherever your payload is going to be. So exploit right here, that would be, payload would be another word, commonly used word for that. Alright, so hopefully that helps you just a little bit further in terms of some of the mindset that we need to have as we tie everything together. It's easy to get focused on one thing, like a stack pivot or a ROP or SEH overwrite, but we have to make sure that they all tie together and they all work exactly. So at the end of the day, we do our SEH overwrite, we do our ROP chain to bypass our DEP, and then we need to be able to go and do our shellcode. Okay? So coming up, we will be learning more in detail about shellcode, how we can write and create our own shellcode and not be reliant upon others. And so we'll be spending some more time on that. And we'll probably have another ROP exercise where we'll just do some ROP and we'll have some shellcode, probably an egg hunter. We'll probably also have another exercise where we'll just focus purely on shellcode. So we'll catch you next time, and good luck.